Hi everyone, and welcome to our Tuesday walkthrough on supervised versus unsupervised learning, K-nearest neighbor, and naive Bayes. Let's get right to it. In this video, we will talk about what supervised learning is and what classification is. We will talk about how K-nearest neighbor works and how naive Bayes works, and then we'll walk through, obviously, the code for it. Now let's get started with supervised learning. Supervised learning is basically the whole idea that we give our algorithm a specific set of categories into which to sort our tuples based on the input data. Let's take a look at this great video.
Supervised learning, as the name suggests, works under supervision. That is, it's a learning in which machine is trained with data which is well labeled and then predicts with the help of the labeled dataset. But what is a labeled dataset? Data for which you already know the target answer is called a labeled data. Like I show you an image and tell you that it's a dog, then it's a labeled data. While if I show you an image without telling you what exactly it is, then it's an unlabeled data. Now let's say we have images which are labeled as spoon or knife. We then feed it to the machine which analyzes and learns the association of these images with its labels based on its features such as shape, size, sharpness, etc. Now, when a new image is fed to the machine without any label, with the help of the past data, the machine is able to predict accurately and tell that it's a spoon. Hence, in supervised machine learning, the algorithm teaches the model to learn from the labeled example that we provide. So supervised learning can be further divided into classification and regression. It is a classification problem when the output variable is categorical, such as red or blue, disease or no disease, male or female, whereas it's a regression problem when the output variable is a real or continuous value. For example, salary based on work experience, weight based on height. So it creates a predictive model showing trends and data. So now if I say, will I get a salary raise or not? That's classification. But if I say, how much salary raise will I get? That is regression. Now let's understand classification with the help of an example. In order to predict whether an email is a spam or not, first we need to teach our machine what a spam mail looks like. This is done based on a lot of spam filters, like firstly reviewing the content of the email, then review the email header and search if it contains any falsified information. This is done based on some keywords like free, lottery, price claim, etc. Then general blacklist filters to stop emails that come from already blacklisted known spammers, and etc. So all these filters scores the email which is known as spam score. The lower the total spam score of the email, it is more likely that the email will land in subscribers' inboxes. So based on the content, labels, and spam score of the new incoming mail, the algorithm decides whether it should land in inbox or the spam folder. Now let's quickly understand regression. So let's say we have two variables, that is temperature and humidity, where temperature is the independent variable and humidity is the dependent variable, such that as the temperature increases, humidity decreases. Hence, they are correlated. When we feed this data to a regression model, it will understand the relationship between these two variables and how one variable depends on the other. After the machine is trained, it can easily predict the humidity based on the given temperature. Well, that was about regression. Now, let's see some real-life applications where supervised learning is used. So, supervised learning is used in risk assessment to assess risk in financial services or in insurance domain to minimize the risk portfolio of the companies. Image classification. Facebook recognizes your friend in a picture from an album of tagged photos. So, image classification is one of the key use cases of demonstrating supervised machine learning algorithms. Obviously, a lot more goes into all these, like convolutional neural networks, etc. Fraud detection, whether the transactions made by the user are authentic or not, and visual recognition, the ability of a machine learning model to identify objects, places, people, and actions in images.
So to summarize, classification is the problem of identifying which of a set of categories an observation belongs to. In order to conduct classification, we typically follow 6 steps. The first of these steps is to determine what the class attribute in the dataset should be. That is the class attribute for classification. That's the attribute that we're going to predict later on. And of course, since we're doing classification, we're going to want to make sure that it is a categorical attribute here. So this also means that we need to pre-process the data in order to ensure that the dependent attribute is categorical. This may involve removing the NAs and transforming the data types as needed. Then we're going to split the data into a training set and a test set. And we're going to build our model based on the training set, because the training set helps us to build the model. And then we're going to test the model on the test set to see how good it is, which means that we're going to compare the calculated class values to the actual class values that we already know in the test set. And that way we can determine how well our model will function if we use it on unknown data. So for our purposes, we're going to start with a data set that has a dependent attribute that is categorical. For our purposes, we're going to use an insurance data set, and we'll take a look at that in a little bit. The first thing we need to do is import all of our libraries again, and we are going to also import our insurance data set, which is here as insurance with categories, and then we're going to take a look at this data set. All right, so here we can see our data set with age, sex, BMI, whether someone has children, whether someone is a smoker, what region someone lives at, and the insurance charges previously incurred. So we can see here, age, of course, is numeric. Data type, sex here is categorical binary, BMI is numeric, children is most likely numeric, smoker, yes, no, is binary, region would be categorical, because obviously southwest, southeast, northwest, northwest, there's got to be a northeast and that kind of thing. And then charges here is numeric. So let's first talk about k-nearest neighbor. K-nearest neighbor is based on assumptions that you make every day that something is like something else. So for example, you meet a group of stylish, young, sportive people with expensive cars from a certain neighborhood, and then you hear them talk about their friend Ben. So you would imagine Ben to be just as young and stylish and sportive and maybe driving an expensive car as this first group is, right? And you learn then that Ben lives in a neighborhood where people have an average income above $200,000 and they do drive fancy European cars. So most likely Ben will drive an Audi or a Porsche or a Mercedes or maybe a Lamborghini, right? The point here is that you're going to want to know how many people you have to meet from that circle of friends in order to be comfortable enough assuming that Ben is in fact a Mercedes driver or a Porsche driver. And that is the K. That predefined number, the K, is the number of training samples that's closest in distance to the new sample that we want to classify. And the label of the new sample will be defined based on these neighbors. So the label of the new sample would be, for example, Audi, Porsche, Mercedes, or Lamborghini. So how does k-nearest neighbor work? Well, first you're going to have to load the data, and then you're going to have to initialize k to your chosen number of neighbors. That is the number of neighbors that you choose in order to make you feel comfortable that your judgment about Ben is based on a solid set of assumptions. So if it's 5 people that you have to meet in order to determine that Ben is most likely an Audi driver, that would be okay. If it's 12 people you have to meet before making that assumption that Ben is also an Audi driver, your K would be 12. So then for each example in the data, you would calculate the distance between the query example and the current example from the data. You would then add the distance and the index of the example to an ordered collection. How that works, we're going to see in a bit. Then we're going to sort the ordered collection of distances and indices from smallest to largest. And we're going to pick the first k entries from the sorted collections. And then we are going to get the labels of the selected k entries, and then we're going to also return the mode of the k labels. Now, all of this sounds really theoretical. This is what we're about to do. In order to work with the k-nearest neighbor algorithm, we use its library from the scikit-learn package. And just because we can, I'm going to show you a really cool new way to build training and test sets with a process called cross-validation. And I'm also going to show you a really great way of conducting exploratory data analysis. So before we go into exploratory data analysis, or EDA, we're going to import matplotlib, the patches, and pyplot, because we're going to need this later on. And then we're going to import from scikit-learn our neighbors and our data sets, and from model selection, we're going to import cross-validation score and train test split. We're going to use this in order to do cross-validation beforehand. All right, so now let's talk about our EDA. The first thing we're going to want to do for the insurance data set is we're going to want to see what our data set looks like. We're seeing here that we have a length of 1338 rows in this data set. We have 7 columns here, age being column 0. And we have these data types here. Object is, of course, categorical here. All right, so we have 4 numeric attributes and 3 categorical ones. Now we're going to rearrange the numeric features into a data frame and use them to predict what region the person comes from. So remember that the region here, our southwest, our northeast, etc., that's what we're interested in. And then region, in our case here, if that's what we want to predict, that becomes our class attribute. So here I'm going to build a data frame called insurance2, and I'm going to pick age, BMI, children, charges, and region. And then that gives me this data frame. And just so that we know what the levels of region are, or the different labels of region, let's take a look. It's southwest, southeast, northwest, and northeast. Okay, so we've got 4 categories here. That's what you're seeing right there. So we could stop here, but why? I'm going to take a few moments to introduce you to a really, really awesome package that makes your EDA much easier. It's called the Y-Data Profiling Package. Previously, it used to be called the Pandas Profiling Package. It's not a standard package, so you're going to have to install it with pip. And you will see directly what it can do and how it can make your life in terms of exploratory data analysis so much easier. So the first thing we're going to have to do is to run our pip install -u ydata-profiling, and we're going to install this for Notebook because this is a Jupyter Notebook that runs on Google Colab, and then with Unicode. So this installation will give you a whole log that displays in the screen. And the first thing that you are going to be seeing is that you are going to be asked to restart the runtime. And that's what we're seeing right here. So I'm going to click on Restart Runtime. This will also then remove any kind of variables from our memory. So we're going to have to rerun our previous analysis. All right, so I restarted the runtime. And at this point here, I'm going to re-import my libraries and my data set. And I'm going to re-import my KNN. I don't need to do that because that's not importing anything. I'm going to rebuild my insurance2 data frame. Okay, so, and now from Y-Data Profiling, I'm going to import the profile report. And that's what we're going to run on insurance2 with and that's the Insurance 2 data set that I just built up here. And we're going to run that as the Insurance 2 profiling report. It's going to take a moment here, and you can see already how it is analyzing the data without you really having to do anything. So the Insurance 2 profiling report, you're seeing here dataset statistics, number of variables, missing cells, duplicate rows, total size in memory, variable types, etc. What are the variables? For example, the age variable, how is it distributed? How is, what's the minimum, maximum, and so on and so on. What's BMI? How is BMI distributed? Oh, that's a nice curve here. What kinds of children do we have? What are the charges? And so on and so on. And then you can also take a look at interaction between, for example, age and charges, or BMI and charges, and you can see already that you can see correlations happening because you get a scatter plot here, right? So super cool. You can look at an automatic heat map here for correlations, and you can look at the correlations in a table. This is your correlation table from last week. And then do we have any missing values? And of course we don't here, so that's a good thing. And then here you can look at a sample of the data. That can come in very, very handy, especially when you are trying to analyze a larger data set that has more than 1,300 rows, but that has maybe 1 million rows or so. So super cool here. Again, this is the Y-Data profiling package. Try it out, click around. It really will show you a lot of good stuff. Now that we've done our EDA, let's set up our training and our test sets. Remember, we use a training set in order to train our model, and then we use a test set in order to determine how well our model is performing. So we are going to set up 2 variables here. The first variable, we are going to just call it X because we can, is the first 4 columns of the Insurance 2 dataset, and that is here all the numeric columns. So age, BMI, children, and charges. And then my Y attribute, which is the one that I'm going to predict, that is also my class attribute, is going to be the region attribute. So that's going to be my Y. I'll show you that here. See, region. So these are the class labels. So we can print our X and we can print our Y to see. Here we go. These are our X's. This is our Y. All right. So we verified our class labels. Let's move on. One of the easiest ways to split a training set from a test set is to use the train test split from sklearn model selection. For that, we're going to set this up like as follows. We're going to say xtrain, xtest, ytrain, and ytest in that sequence. That's very important because that's how this command is configured. So then we are going to say train test split, x, we saw what x is, y, that's y here, and we're not going to randomize. So that will set up automatically a 75% training, 25% test split. That's the default setting for train test split. So then we can print our shapes here, and I've already done that. So my xtrain shape is 1003, and of course it has 4 columns. And my ytrain shape has, of course, the same number of rows, but it has just 1 column because that's this here. So how would you get the rows and columns that you have in the test data set? Remember, you have your X test and your Y test here. How would you display these below? All right, so let's then delve into it. We're going to build the simplest model with a K equal to 1, which means you need one nearest neighbor. You're looking at just one nearest neighbor in order to determine what your test data is supposed to look like, what category your test data is supposed to be. So for that, we're going to import from sklearn-neighbors the k-neighbors classifier. And we're going to set up our model. In my infinite creativity, I'm calling this model 1. And we're going to pull the k-neighbors classifier here with the number of neighbors set to 1. And that is your k. And then we're going to fit that model with model1.fit on our x train and our y train. Remember, x train and y train. And that's pretty anticlimactic because you're really not seeing anything until you test it. And that's what we're going to do right here. So the first thing we're going to do is set up a variable called ypred, which is a variable in which we're going to store our predictions. So we're going to use our x-test data set now. Remember the 25%, right? We are going to use our model 1 that we have just built up here. And then we're going to predict based on the x-test inputs what the output for our model 1 would be. And that is my ypred. Those are the predictions. Now later on, we will be able to compare these predictions with our actual y-test because we know those, we have those values. And this is where calculating the quality of your model comes in. All right, so here we are going to run our test set predictions, and that really doesn't give us much. It just gives us the output of the predictions. So the next thing we're going to need to do is really evaluate our ypred that we've generated here in comparison to our y-test, and that's what we're going to do now. One of the easiest ways to evaluate the quality of a model is to calculate the accuracy score. For that, we're going to just print a formatted output here from our model 1. From that, we use the score attribute here. And then we're going to use our x-test because that's what we fed into our model 1 and our y-test. So for that, the test score is 0.36, that is 36%. Ideally, we want a test set score that is much higher so that we can have confidence that our model 1 is really useful. So now let's compare our ypred, our predicted values, with the actual values that we know should have been the results that we have in our y-test. So here, all I'm going to do is a visual comparison. I'm going to build a data frame with my ypred and my y-test. And here we're seeing, setting the column names here. And let's take a look at that. So we're seeing here that northeast was the predicted value. Southwest was the actual true value, the original value. Southwest was predicted when here the original value, the actual true value is southeast, southwest, northwest. Yeah, that doesn't look very good, right? So how can we really get a good overview of the accuracy of our model? Well, for that, we have what's called a confusion matrix. That's what we're going to talk about next. Our confusion matrix compares the calculated or predicted values for all labels in the class attribute with the actual true values that we know. So that allows us to check whether the true values were predicted correctly and which ones were predicted incorrectly. So for that, we're going to use, from sklearn metrics, we're going to use confusion matrix, and we're going to use the confusion matrix display also from sklearn metrics. So, and then I'm going to call my confusion matrix CM, and I'm going to apply my confusion matrix to my y-test and my ypred. And then I'm going to use the class labels from model 1 here. So then I'm going to display with confusion matrix display my confusion matrix that I've set up. And my display labels, that's these here, they come from my model 1 because those are the actual display labels. And then I'm going to plot this. And this is my output here. So we're seeing the true label, that is reality, is on the left edge of the confusion matrix. And that the predicted label is on the bottom of the confusion matrix. And here we have a nice heat map that shows us the quality of the predictions right away. So we're seeing here that, for example, for Northeast, we're seeing that 35 data points that were actually Northeast were predicted correctly as Northeast. However, 18 data points that were actually Northeast, that were really Northeast, were predicted as Northwest. And 17 data points that were Northeast were predicted as Southeast. And then we have 26 data points that really were Northeast. They were predicted falsely as Southwest. So now we can understand that that the accuracy score really is rather low, because what we would expect is to see very high values in Northeast here, in Northwest true, Northwest predicted, which is kind of what we're seeing here, but still Southeast predicted, and Southwest predicted. But what we're instead seeing here is that, look at the predictions for Southwest here. They're all over the place, right? So Southwest here, 17 that are Southwest were predicted as Northeast, 13 that are Southwest are wrongly predicted as Northwest, and so on and so on. The last method of predicting the quality of our model is what's called the classification report. The classification report gives us 4 values based on each of the categories. The first value is precision. Precision is the number of correctly identified positive results, that's the true positive, divided by the true positives and false positives. Or it answers the question, for all instances classified positive, what % was correct? And that's what you get with this math. And that's what you're seeing right here. Then you have recall or sensitivity, which is the number of correctly identified positive results divided by the number of all samples that could have or should have been identified as positives. So you have the true positives divided by the true positives and the false negatives, so the ones that should have been positive. So in other words, recall answers the question, for all instances that were actually positive, what % was classified correctly? And then you have the F1 score, which is the harmonic mean of precision and recall. And support is the number of actual occurrences of the class in the data set. So these are the actual labels, class labels, as they appear in the data set. So here's what the code looks like. From sklearn-metrics, we're going to import classification report. And then we're going to print the classification report based on whitetest. That's from our original test data set, and our whitepred. Those are the predicted values. We're going to use the labels Southwest, Southeast, Northwest, and Northeast. And what we're seeing here is, in terms of precision, that is the correctly predicted positives. We see that 18% of Southwest has been predicted correctly, 42% of Southeast, 43% of Northwest, and 41% of Northeast. So if you think about this in terms of more high-risk data, for example, a car brake engagement, automotive brake engagement, that would mean that here your brakes, if you step on them in your car while driving, would engage in 18% of all cases. So, it always depends on the context. of your data, whether the precision values, the recall values are really acceptable. So how can we improve our model so that it shows us better values? Well, for one thing, we can increase the number of K so that we look at more of our neighbors in order to determine what the label of our unlabeled data should be. Let's do that. So here we're going to build our K nearest neighbor with 5 nearest neighbors instead of 1. And then we're going to, just because we can, set up a 2/3 to 1/3 training and test split. Maybe that also helps. First things first, we're going to use our test size parameter here with a train test split this time to configure that to 0.33. The whole idea being that we don't want the 75/25 default setting, but we want the test size to be 0.33 so that we get 0.67 as the training size. And then we can print our shape here, and as we're seeing, our training, our test sets are of a different size here. So now let's build our model with K equal to 5. So our model 5 is going to be neighbors.kNeighbors classifier. We already know that, but now we're going to set the n neighbors to 5. Then we're going to fit our model 5 on xtrain and ytrain. And then we're going to set our ypred to our model 5.predict on xtest. This is no different from what we've done before. So now let's take a look at the confusion matrix and the classification report, because that gives us a really good visual representation of the results. So here we're seeing for northeast, correctly predicted as northeast, this is still really not very good. We have here 71 out of 104 that are predicted incorrectly here for northeast. So that's not really good. Our results have improved a little bit for northwest. I'm seeing a 42 here for the true label versus the predicted label. Let's compare that with the 33 that we saw before here, northwest, right? Here for southeast, we saw 38 that was predicted correctly. Let's see what that looks like now. Now we have a 41 here, so also a little bit better. But for southwest, it's still, you know, the number of correctly predicted items has not changed from 15 to 15. The only thing that has changed a little bit is the allocation to the other categories here. So for Southwest, our K of 5 has not made a big difference. The biggest difference that we're seeing in the quality of our model has been for Northwest and for Southeast, and then a little bit for Northeast. So let's take a look at what we're seeing here. So for Southwest, our precision has gone up from 14 to 24%. For Southeast, the precision has gone from has gone to 34%. That was at 42% beforehand, and for Northwest at 43%. Okay, so these values have declined, and then for Northeast, we're at a 28, where previously we were at a 41. That's obviously not optimal. We tried K equal 1. We didn't get a very good result. Now we tried K equal to 5, and we didn't get a very good result either. In fact, our precision went down, and our overall accuracy went down to 30% rather than the 36% that we had before. We could now spend days increasing our K by 1 in order to finally find the correct setting, but really there is a way of finding the K that is much faster and that will give you the optimal setting for K that is called cross-validation. And that's what we're going to talk about now.
Cross-validation is a commonly used technique where we can leverage all of our data and still generate a fair model evaluation. The first block represents our total data set. Every observation we have is represented in this orange block. Now in a traditional data split, we have two sets, a training test and a testing set. With cross-validation, we split our data into partitions, known as folds. These folds aren't immediately designated as training or testing. We want to pick how many folds we will split our data into. Common sizes are 5 or 10, but that's to your discretion. You can see in this example, I chose to create 5 folds. Each fold will contain the same percentage of the total data. You will not see the same observation in 2 different folds. A given observation can only show up in one fold. What we do is create K models where K is the number of folds. So if I created 5 folds, as I have here, I will create 5 different models. In each model, I will test on a different fold, using the remaining folds as training data. So for example, if we look at model 1, you can see I will train my model on folds 2, 3, 4, and 5, and test my model on fold 1. For model 2, I will train on fold 1, 3, 4, and 5, and test on fold 2. So hopefully you get the idea. After building each model, I can evaluate the results on each model's test set. Here you can see I've returned the accuracy score of each model. Because I have built 5 models, I returned 5 accuracy scores. The significance of cross-validation is I can average those scores to get a more accurate evaluation. In this case, I return a cross-validation accuracy of 80.8%. The most common reason we use cross-validation is in scenarios where we have a limited amount of data. Consider we have 100 observations in our data set. We want to use as many training observations as possible, considering we already have such a small data set. So let's say I choose a 90-10 data split, as I'm concerned with the model seeing enough data. From that standpoint, it makes sense. However, we would only be left with 10 observations to test our model. With such a small number, it is not reasonable to gauge the effectiveness of our model. With one group of 10 test observations, our model may look very strong if we got 9 correct, which represents a 90% accuracy. However, if we use a different 10 observations, maybe our model would have only gotten 6 right, and our model would seem pretty weak, returning an accuracy of 60%. There just isn't a big enough test set to make a fair assessment. That is why cross-validation can be so useful. In doing so, we can get a fair prediction for all 100 observations to improve the reliability of our results. So you may be thinking, okay, so now I have 5 models. I only want to use one model to make my predictions. How does that work? Well, we're not going to use one of the cross-validation models for predictions. Cross-validation is only for model evaluation, not for model building. Once we have a fair evaluation, we can go back to our full data set and train our model on 100% of the data.
All right, so now that we know what cross-validation is and does, we're going to apply it. The first thing we're going to do is build a K list. That is a list of potential values for K that we're going to cycle through the algorithm. Then we're going to collect the accuracy scores, and then we're going to sort the accuracy scores, or rather, we're going to calculate our errors, which is 1 minus the accuracy scores. We're going to sort those, and then we'll be able to find our K with the smallest error. That's what we're going to do. So I'm going to set up the K list here with a list of a range from 1 through 50. The list grows in increments of 2. So 1, 3, 5, and so on and so on. And then we're going to create an empty list that's going to hold our cross-validation scores. So I've already run this, and as you can see here, when I hover over this, here are my cross-validation scores that I've already stored in my CV scores. So now that we have our list and that we have our CV scores, we've got everything set up, we can start working with it. For that, we're going to build a little loop here that loops through the K list. And I'm going to say, well, model 10, I'm just going to call it model 10. I'm going to use my neighbors, K neighbors classifier, which is my classifier. And then my number of neighbors is K. Where does the K come from? Well, the K comes from the K list, and the K list increments from 1 through 50 in steps of 2. So then I'm going to use scores to store my cross-validation score for this model here, for my X and my Y, with my cross-validation set to 10 because I want to do a 10-fold cross-validation, which is one of the most frequently used cross-validations here. And in order to score my my different models that it develops, I'm going to use my accuracy here. So for that, I'm going to say, well, CV scores, which is up here, I'm going to append to that. So I'm making an array. My scores here, and I'm going to use the mean. So now I'm going to change my accuracy scores to the misclassification error. And basically the misclassification error is just the opposite of my accuracy score. So my errors are going to be 1 minus my NP array of the CV scores. All right, so now we can use that error to determine what the optimal K is. So let's take a look at our errors and see what happens. I'm going to set up an optimal K here, and I'm going to go through the K list here, and I'm going to then pull out my errors with argmin. Argmin here, argmin returns the indices of the minimum values along an axis. So we are going to basically sort our optimal K based on the errors. So which means that since the 1 minus the CV score is going to be the value by which we're scoring, we're going to get the smallest error first because we are doing a 1 minus the highest accuracy score with the argmin. So, and then I'm just going to pull out the optimal number of neighbors is, and then I'm going to pull out the optimal K. So, and now I can also plot that misclassification error versus my K. And for that, I'm going to plot my K list, this K list here, versus my errors. And then I'm going to, on my x-axis, name that number of neighbors K, and on my y-axis, I'm naming that misclassification error here, and then I'm looking at the plot. And we're seeing the optimal number of neighbors is 1. Well, does that surprise us? It probably doesn't, because we've already seen how the scores for a K of 5 are really not better than the scores for a K of 1. So here we have our mathematical proof that as we plot our misclassification errors, here we're seeing that the misclassification error for 1 is the smallest right here. All right, and now it's your turn. Rerun this model with a K of 10 or a K of 5 or a K of 20 and a K of 50, and then see what happens with your confusion matrix, see what happens with your classification report, and see what your results say about the data. Now that you already have the answer, it's really interesting to see what errors and what mistakes you can identify. And at this point, we're done with the walkthrough of the K-nearest neighbor section of this file. The next video will give you the walkthrough through the naive Bayes section of this file. See you in a bit.